Hello, and welcome back to the course on distributed systems and security. We have made it to replicated state machines, um, which is the topic covering replication of services. So we already at some point touched lightly on how we could replicate a file, for example. We would put it on 3 machines such that we could access it even if one of the machines were down. We would try to read from all machines and wait until we get 2 machines reporting the same file, for example. So one step up from that is, instead of replicating something static like a file, we would like to replicate a running service. So I would like to have a database or a web page or something which is constantly evolving, running on 3 different machines and being consistent, with the goal that if one of them is down, I can use one of the other 2. Or if one of them is corrupted and actually tries to manipulate the service, I can use the other 2. There are some complications in that, and we will cover that in this lecture. First, we'll take a look at how to define the problem. What do we want from a service like that? That is called replicated state machines. Then we will look at how to build replicated state machines using totally ordered broadcast, and see that that is the core of the problem. And then we will turn our attention to building totally ordered broadcast. And we'll in fact do that in 3 different models. We'll do it in the synchronous model, we'll do it in the asynchronous model, and we'll do it in the eventually synchronous model. And eventually, along the way, we will also cover the topic of group change, which is if a service, if one of these servers is crashed, how do we gracefully remove it from the group of servers running the service and adding a new one? And ultimately, we might even imagine over time growing the number of servers running a service or shrinking it depending on network conditions. So group change is the topic covering that. Okay? But let's start by jumping into what do we mean by replicated state machines and getting the basics in place. So as I already said, imagine a setting with a database. There's some database sitting, and anyone can read and write from the database. So it's an evolving piece of data. And it's critical for our system. It might crash and become unavailable, and we don't want that. So we just make 3 copies of the database. Now people can read and write to whatever copy they want. And then if one of them crashes, we have the 2 other copies to look at. There's an obvious problem here, of course, that what if different clients write different stuff to different databases? I mean, soon they will drift apart and be just 3 independent databases, and then we just have another problem, namely inconsistency. Well, replicated state machines, the theory around that is the theory solving exactly that problem. Yeah. So for now, let's just say we know at least how to replicate. We make 3 copies of the database, but then what? There's 2 things we would like from a system like this if we're just looking at the interface that it's offering us. So the way we want to look at a replicated database is, I, for example, have 4 copies inside here of the database sitting on different physical machines, and they can talk to each other and try to kind of stay consistent. So we want to put the job on staying consistent on these copies of the database. And then there will be a common interface here where clients can read and write, say, from the database, or give inputs to the system and see outputs in general. It could also be a web page where I put something in my shopping wagon, and then I can check it out and it updates. And if I log into, Amazon a week later and I get another server, I want to see the same view. Yeah. So it's clients here moving maybe between replicas. So what we want is that this one interface here that makes it look like one system. So it should look like one system from outside. So if I write a variable with 7 and then I read it afterwards, I should see 7, or maybe some other value that would update it, but it shouldn't be lost, and my view shouldn't depend on which server I'm looking at. So that's kind of our vague definition right now of consistency of a system like this. Then there's two levels in this. In fact, there's many levels, but there's two very common levels to consider. Which one is server consistency and one is client consistency. So the server consistency, which is what we will mostly look at, it is the property that these servers in here, these 4 servers here, will eventually become consistent. By eventually, I mean they might not always be in the same state. I mean, they can't on the millisecond all take the next step in the computation, so to say. Sometimes one will take a step first and then the other one. But what we require is that if some server was in a particular state, had a particular state, I mean, the contents of my shopping reckon, right? Then all other servers that will also pass through having the same state. So eventually they will catch up and have the same state. At this point, this could have progressed, but then they will eventually catch up with that thing again. So this is what we call eventual consistency in systems like this. Systems out in the wild that you might know is, for example, the DNS system. It has eventual consistency. If I update which IP address corresponds to one of my URL names or my domain names, it will take some time to propagate through the system. But if I make an update and then for long enough don't change the system, eventually everyone will see the same thing. So that's what we want from the server. They are eventually in the same state or pass through the same states. Now, this thing that one server is allowed to be a little bit behind another server, that could potentially be very confusing for a client. Let's say a client was over here writing a file, and then it leaves, and then later it logs onto a server here that didn't see that update yet. Then the client would see an earlier version of the file it was writing. That could potentially be very bad for the application using it. And this actually happens sometimes on the university home servers for me. One of the places where one can see it, for example, if you're editing your homepage, you're editing the HTML and you're saving it, and then you go and load the page in the browser, and then it's an old version of the homepage, and then sometimes it takes 30 seconds before you see the update. And that can give some weird behavior. You do an edit, you update, and you see nothing changed, then you edit more, and suddenly the changes start coming through. And the reason for this is when you're editing your homepage, at least if you are sitting at the university, you would be behind the firewall, and you're sitting and editing on some file servers. And then eventually these changes are put out on the other side of the firewall onto the web servers that are showing these home pages. So it actually takes time to propagate in this distributed system. And one is not always aware of that. And that can give these weird behaviors. So that's another thing to consider in a system like this, that even though the servers eventually pass through the same state, if you use a distributed system like this as a client, probably need to do something else to not be caught off guard and seeing old versions of a file. So in the lecture here, I will mostly talk about server consistency because that's the hard part and therefore the fun part. And then you will see in the book a few exercises about how to get client consistency. Get some settings and see if you can argue about how it can be solved or whether it can be solved in that setting. Yeah. Okay, so that's the setting. We would like to get some replicated servers being consistent. So there are many ways to implement this. There's also some doing it loosely, such that the systems are not necessarily ever consistent, but they're consistent enough for the application to get efficiency. But what we have decided to do in the book is to implement an example with very simple semantics. So we want to give you an idea how this works. And therefore, it's good to take a setting where it's very clear what we want to do. So we go for this eventual consistency where all servers are consistent. They will go through the same sequence of states, maybe just with a little bit of a delay. And there's one very common way to do this. A lot of ways to do it can be viewed on this form here. So what you do is you write down the service you want to run, your database, your web page and something, and then you write it down as a deterministic system. And by that I mean it's a system where there's a unique start state, the database is empty, boo, 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 boo. And then you should have the system that if you start from the same start state and you run this system on the same sequence of inputs, then it ends up in the same state again. Okay? We call that a state machine. So it doesn't do something weird. It's not that if it's in the start state and get 42, then sometimes it ends up in one state and sometimes in another state. There's no non-determinism. There's no randomness. The state you produce only depends on the inputs you get, and your initial state. And then what you do is you create your distributed service. Let's say you want 3 servers. You start them in the same start state. And then you find a mechanism to ensure that they all see the inputs they're running on in the same order. You're using broadcast for this. So whenever you want to give to this system here an input, you broadcast it. With one of the machineries we have seen in previous lectures, like synchronous or asynchronous broadcast, you broadcast the input so they all see the same input, even if there's malicious behavior in the system or crashes, and then they run on that input. And then the next input is being broadcast, so they run on the same sequence of inputs. So that means you end up guaranteed by these 2 mechanisms, deterministic service and broadcast, having the machines going through the same sequence of states. They might be a little bit delayed because there might be a delay in physical time between when they see a message being broadcast, but they will eventually see the same message and therefore go to the same state at this point. Now, it actually turns out it's easier said than done, this thing of programming a deterministic system, because in many programming languages, I mean, there's non-determinism in the libraries. Libraries are underspecified. For example, if you have a set of elements, then the interface is you can add an element, and then you can ask to iterate over all the elements. And often you're not given any guarantees in which order you iterate, because that will allow more implementations, and therefore you can be more efficient in your implementation. But that also means if you're programming your service here and you're using a set data structure somewhere, and then you run on 2 different versions of the programming language, and the libraries are on 2 different operating systems, when you start iterating over the outputs of the set, you might get them in a different order. So if you take them out, let's say that's the next batch of inputs coming, it comes as a set, and then you just iterate over them and run on them, you might have 2 servers diverging. One should avoid that non-determinism, randomness, anything in programming. So it's not as easy as to do as it is to say, but that's just for now say that's a practical problem. You have to program your service such that if it starts from the same state and goes through the same inputs, it always ends up in the same state. And in particular, it gives the same outputs. Then we can do it, and that's kind of the skeleton for doing it. So when we want to be highbrow about this deterministic services, we call them state machines. So a state machine is just something with exactly that behavior. It's something that has a well-defined state. It can take an input, and then depending on its state and the input, it will produce an output, and then it will change to a new state. And it's well-defined, it's completely deterministic. We use the abstraction in the book, so let me just go over it here. Okay, so a state machine, as a formula, it's something that has a set of states. That's the possible states it can be in. I could think of that as the database. There's an initial state called state 0. It's one of the states. Then there's a set of possible inputs. So the inputs come from this set here called inputs, and can in each activation, as it's called, give a single output from the set here of outputs. And then what it is doing is just defined as a function. So given a state and an input, it outputs a state and an output. And that's what catches the determinism, because it's a function. It really just maps always to the same element. And that's what there is to it. And then sometimes we abstract away the state and just say, I mean, if I have a machine in some state and I say run it on an input, what I really mean is fetch the state, run on that input, save the state, and then give the output. So then we can think of this function here as defining a machine. In particular, we write it like this here. If I have this machine M here and I say I'm applying it to the sequence of inputs, it means start M in the initial state, then run on input X, that gives some output y1, then run on input x2 from the new state that was produced that gives y2, save the new state, and so on. And in each step, you use this transition function here. So you should write down your system so it can be thought of as being on that form. Okay? Yeah, that's what there is to that. Then we can say a little bit more about what we would like our system to do now. So when we specify our replicated service, we will specify it using a state machine. So I'm going to write down a single state machine, and that one defines what I want my service to do. The intended behavior is something that is running that state machine just on a single machine. So there is no inconsistency. But now I know I have to replicate it. And I will have several machines running the same service. So what do I want? The first thing we want is that we're going to get now a distributed system here where inputs are given and outputs come out. And I want, as we usually do, to specify the consistency of the system here just by which inputs and outputs it's producing. So what do we expect from it? Well, what we expect from it is that the outputs it's giving is consistent with having run this state machine here. Okay, I mean, some inputs could be given here, some inputs could be given here, some here. So I mean, what this client sees as outputs, let's just say all clients see all outputs, should be this state machine here run on the inputs that have been given in some well-defined order. But definitely, I mean, just something that could be resolved from running this machine. Okay, so that's what we call validity. We say that if a client saw a sequence of outputs, then they could be produced by running this machine here on some sequence of inputs. So that just means the outputs are always valid. They're consistent with some run of the machine. Huh? And then we would also like agreement, which is that if one honest service sees some sequence of outputs and another honest server sees another sequence of outputs, and this one is shorter, so m is less than or equal to m, then this here should be a prefix of that one up there. The shorter one should be a prefix of that one. So if I take y1 up to yn and instead write y1 up to ym, the lesser integer, that should equal c1 up to cn. Okay. So when phrasing agreement, we shouldn't fall into this trap of saying that the sequence of outputs by two servers are the same, because again, there could be a delay. There's one that gets the output last. But what the way to say it is to say that the shortest one is a prefix of the other one. And that means it always have the chance to grow up and be the same one. But then this could have grown also. But this one will always, at any point in time, be a prefix of the other one or the other way around. That's what we mean by agreement in a system that's continually getting inputs and giving outputs. Then there's other properties you would like to add here. For example, of course, these inputs over here should not just probably be any kind of inputs. It should be the inputs that were actually given to the system. Maybe we also want fairness such that if inputs have been given by these three up here, and they're all giving 1 million inputs, then it doesn't happen that we keep selecting only the inputs from these here, that the sequence is 2 million long. But this client here sometimes get its inputs considered too. But these are mixes of liveness and safety properties, so we have left them out. In particular, there's nothing in what we do here in the slides or in the book which prevents actually ignoring all inputs from a particular client. And then that we have, I mean, we cover that later when we talk about Nakamoto style consensus in a bit more detail. But it's just because it's annoyingly complicated to specify, and it's rather obvious when we look at the protocols that they do have this property. Okay, so let's not specify that. Let's focus on the two interesting one, namely validity. The system is consistent with running some machine, and all honest services are getting the same sequence of outputs. Okay. Here, I think it's an example where actually specifying what we expect from the system is easier as an ideal functionality. So we have that in the book too. So another way to specify the system, right, is to specify a single agent that is kind of describing exactly what is the input-output behavior of this thing in here. This is what we have called an ideal functionality, right? So let me iterate again. Let me try to specify again. So in terms of ideal functionalities, what is a replicated state machine? Okay. So it's a replicated state machine. It's supposed to run this service here. What do we expect from its inputs and outputs? So we're going to give it some ports for this. So I mean, it will take its inputs here. So the input from server I come on this RSMI port. And then when an input arrives, because we want to model that we're not hiding the inputs, we'll just output on the corresponding receive ports to the adversary or whoever is sitting up there that here this input was given. That just models that we're not obliged to try to hide the input. And then when the input comes, we will just for now store it in this set here called unprocessed. Those are the inputs that we have not gotten around to process yet. And then when the adversary inputs here on this port process saying, please process this input. Let's see it here. If there is an input X and process is sitting up here, so it's a special port that comes from the adversary, where X is one of the unprocessed inputs. So some party gave this input at some point and it ended up in unprocessed. Then what we will do is we take our little state machine, we take the current state, we run it on X, and we write down the new state and this output Y. So see, we start by this state here being the initial state up here. So whenever we get this input here on process, we just one click of the state machine. And then there are these queues here, these are output queues. So each server has its own output queue initially empty. And then whenever we run the state machine here, we take this output and we add it to all the queues at the end. And then we deliver the queues to all the parties, I mean, from the front. And since whenever we add something to one queue, we add it to all of the queues. They will be building the same sequence. So they will all get the same sequence, but they might just get them at different times. And that's what this last port is for. So each server has a deliver I port that the adversary controls. And if there's any input on deliver I, we'll take the front of this QI here, unless it's empty, remove it from the queue and then output it. Okay? So this is kind of trivially a system that behaves as we want it. We give it some inputs. We don't want to specify in which order these inputs are processed because that's hard to implement, and we want a simple example here. So we just say when an input arrives, it's put into the set of unprocessed inputs. The adversary then gets to pick some of them and say, process that one, process that one, process that one. Also gets to ignore some of them if he wants. And then whenever that happens, we just take the corresponding output that the state machine produces on that input, saves its state, and then we output that to all of the parties, but with some delay by putting them into these queues here that the adversary gets to determine when the elements are output. Okay, so that's what we want to implement. Yeah, you see that here, and then not all servers see all the inputs, but all the servers in this service will see all the outputs from the system. That's a simplification too. We could have some kind of subscribe mechanism where you only want to see some outputs of a special form, for example, the ones in your own shopping bag. But again, let's make it simple, okay? So let's try to implement that. That definitely looks like a replicated state machine, right? Everyone sees M run on some sequence of inputs and they all see the same outputs, okay? If we can do that, we can do many other things. And we can make it more efficient and more refined.